Welcome to The Explainer. Today, we're diving right into a topic that completely flips everything we know about traditional programming right on its head. We're unpacking the wild world of hardware engineering, figuring out together how we actually bridge the gap between human thought and physical electrical reality. We're going to explore where this tech started, how it evolved into a massive global standard, and look at the actual code that makes it all happen.
Now, if you're used to writing software, this question might seem like a total paradox, right? We usually think of code as something ephemeral, just instructions floating around in memory. But it's the exact problem hardware engineers solve every single day. I mean, how do you type characters on a keyboard and somehow end up with a physical, microscopic arrangement of silicon that calculates, processes, and literally powers the very screen you're looking at right now?
Section 1. Hardware versus software. To really wrap our heads around how we do this, we need to draw a hard line between sequential instructions and physical behavior. If you write a script in a language like C or Python, you're basically telling a pre-existing computer what to do, line by line. Step 1, do this. Step 2, do that. But Verilog, it operates on a completely different plane. You aren't giving instructions to a processor, you are designing the processor itself. You're describing exactly how physical components are wired together and how that entire circuit should behave when electricity flows through it.
And that's exactly why Verilog is what we call a hardware description language, or HDL. It's a highly specialized language used to design and model digital electronic systems instead of software. It essentially lets us conceptualize and model incredibly complex digital systems. We're talking literal billions of transistors here, long before we ever have to pick up a soldering iron or send a design off to a multi-billion-dollar fabrication plant.
Moving to Section 2, Writing Code for Circuits.
Let's actually see what this looks like under the hood. Here is a beautifully simple example of a Verilog module for an AND gate. We define our module, name it AND_gate, and then we define our physical pins, input A, input B, and output Y. Then comes the real magic line. Assign Y equals A and B. The output Y is quite literally the physical AND logic of inputs A and B. We close it out with end module. It looks exactly like standard software, but it represents actual physical logic gates.
Because of that, this code doesn't just run like a regular software program. Instead, it's used to design complex digital circuits, things like adders, counters, or entirely new CPUs. Engineers use it to model hardware before physically building it, and, crucially, to test that circuit's behavior using simulation. They also use it to program reconfigurable devices called FPGAs, field programmable gate arrays. These are basically blank slate chips you can mold into whatever hardware configuration you want just by uploading your Verilog code.
Which brings us to Section 3, the power of parallelism.
The absolute crucial point that separates this from traditional coding is one specific concept: parallelism. In a physical circuit, electricity doesn't just wait for line 40 of your code to finish before it politely moves on to line 41. Electricity flows everywhere, all at once. That means multiple events, logic gates, and data pathways are all firing simultaneously. When you write in an HDL, you literally have to think like electricity. Everything happens at the exact same time.
All right, Section 4, Early Simulation and Growth.
So how did we even get here? Well, picture the chip industry back in 1984. Designs were suddenly becoming far too complex for engineers to draw out using manual, hand-drawn schematics. I mean, imagine trying to find a typo in a drawing of 10,000 intersecting lines. Absolute organizational nightmare. Enter Phil Morby at Gateway Design Automation. In 1984 and 1985, he created Verilog with one primary goal: to efficiently simulate digital circuits. Engineers desperately needed to verify that their highly complex designs actually worked in simulation before anyone spent millions physically manufacturing a flawed chip.
And the language was a massive hit. Fast forward a bit to 1989, an industry giant Cadence Design Systems acquired Gateway, deeply integrating Verilog into its simulation tools. But you know what the real secret weapon was for Verilog's explosive growth? Its syntax. Morby deliberately designed it to have a highly familiar C-like syntax. This made it incredibly approachable, and it rapidly gained immense popularity among engineers who were already perfectly comfortable coding in C.
Moving on to Section 5, the drive for standardization.
Naturally, with that kind of widespread popularity came the desperate need for a reliable, vendor-independent global standard. You simply couldn't have the entire hardware industry relying on a language completely controlled by one company's specific toolset. So, Verilog became standardized. In 1995, it was officially adopted as the IEEE 1364 standard, making it universally reliable. And as technology marched on, the standard evolved right alongside it. We saw the IEEE 1364-2001 update, which added crucial improvements for better design capabilities, followed by a major refinement and cleanup in 2005.
And that leads us to Section 6, System Verilog and beyond.
As our digital world expanded into the new millennium, chip complexity just skyrocketed yet again. Standard Verilog was fantastic for designing hardware, but actually verifying that the hardware worked perfectly, that was becoming the real bottleneck. So to handle this extreme complexity, Verilog was massively extended. In 2005, it merged with highly advanced verification features to become a robust, incredibly powerful new standard, System Verilog, officially known as IEEE 1800.
So what did this actually bring to the table? Well, System Verilog essentially brought hardware engineering into the modern software age. It added object-oriented programming features, giving engineers completely new ways to structure their code. It introduced vastly superior testing and verification tools and significantly enhanced design constructs. It wasn't just about drawing the circuit anymore. It was about building complex, automated test environments to aggressively poke and prod that circuit in simulation long before it ever went to silicon.
And that brings us to where we are right now. Today, alongside its counterpart VHDL, Verilog and System Verilog remain the absolute core, fundamental languages in hardware engineering. They are the backbone of modern tech, heavily used in FPGA design, custom ASIC development, and the design of the incredibly complex processors and systems on a chip, or SoCs, that are literally powering the smartphone in your pocket, the laptop on your desk, and the servers running the internet right now.
Which leads us with a fascinating final thought to wrap up this explainer. The famous saying goes that software is eating the world, but when you trace that software down to its physical roots, it all runs on silicon. So if software eats the world, what language builds the teeth? Well, it's parallel hardware languages like Verilog. Thank you so much for joining me on this explainer. I really hope this helped demystify exactly how we code the physical world.